Welcome to today's Explainer. We're going to take some of the most intimidating math concepts out there and literally turn them into super friendly, easy to use cheat codes. If you've ever stared at a page full of tiny floating numbers and felt that cold sweat coming on, well, you are in exactly the right place. Today, we're decoding the laws of indices. By the end of this Explainer, you're going to look at these problems not as roadblocks, but as puzzles we've unlocked the absolute perfect cheat codes to solve.
Here's our roadmap for leveling up today. First, we'll meet the index, then go over the 3 basic laws. From there, we dive into the zero power mystery, demystifying negative indices, and finally, conquering fractional powers. Let's get right into it.
Section 1. Meet the index. Let's kick things off by making sure we all actually know the adorable little characters we'll be working with. What's really kind of cool here is how simple the relationship actually is. Notice that big number sitting on the bottom? That's your base. In our example here, the base is 5. Then you've got that tiny little number floating up in the top right corner. That is the index, or the power. Think of the index as a cute little instruction manual, right? It's just telling the base number exactly how many times it needs to multiply itself. So 5 to the power of 3 is really just a super compact way of saying 5 times 5 times 5. Which, of course, instantly gives us 125. Instead of writing out these crazy long strings of multiplication, the index does all the heavy lifting for us. It's basically math's ultimate shorthand. All right, section 2, the 3 basic laws. Now that we know our players, let's learn the massive, time-saving shortcuts that make up the core rules of the game. Here they are, all together on one beautiful cheat sheet. Let's walk through them real quick. First up, the multiplication law. When you're multiplying identical bases, you don't calculate them separately. No way. You simply add the indices together. Division is the exact opposite. Just subtract the second index from the first. And third, the power of a power law. If you've got a base with an index wrapped in parentheses and that whole shebang is raised to another index, you just multiply those two indices together. And you know, this brilliantly illustrates just how powerful these shortcuts actually are. Take a look at this scary problem. 4 squared all raised to the power of 3. Without our laws, I'd probably try figuring out 4 squared is 16 and then try calculating 16 times 16 times 16 in my head. Yeah, good luck with that. But using our power rule, it instantly reveals itself as 4 to the power of 6, which we can much more easily figure out is a whopping 4,096. Okay, so let's see how this builds into something a bit stranger. I mean, we know what to do with a 2 or a 3 up in that index spot, but what happens when that little index is a 0? Seriously, what does it actually mean to multiply a number by itself 0 times? Section 3, the zero power mystery. You know, most of us just blindly memorize the answer to this back in school. But when we look behind the scenes using the cheat codes we literally just learned, the actual proof is amazing. Take a look at this standard math over on the left. If we divide a number by itself, let's say a to the power of m divided by a to the power of m, everyday math tells us that anything divided by itself is exactly 1, right? 10 divided by 10 is 1. A million divided by a million is 1. But now look at the index law applied on the right to that exact same problem. The law says when we divide matching bases, we subtract the indices, so m minus m gives us 0. That leaves us with a to the power of 0. So, the absolutely crucial point here is, since both of those starting equations were identical, their answers have to be identical too. Putting those two sides together proves perfectly that any number to the power of 0 is exactly 1. It doesn't matter if it's 5 to the power of 0 or a literal billion to the power of 0, the answer is 1. It is just mind-blowing logic derived entirely from our basic cheat codes. Section 4, demystifying negative indices. Okay, so we conquered the 0 mystery, but the math universe has another curveball for us. What about negative numbers up in the index spot? It sounds completely impossible, right? How in the world do you multiply something by itself -3 times? Well, let's use our brilliant 0 trick again. Imagine we have a to the power of 0, and we divide it by a to the power of m. Using our division law on the left side, we subtract the indices. 0 minus m gives us a negative index, a to the power of -m. But let's look at the expanded math on the right side. We literally just proved that a to the power of 0 is actually just the number 1. So the equation is really just 1 divided by a to the power of m, or written as a fraction, 1 over a to the power of m. And there is our next massive cheat code. A negative index isn't really a negative number at all. It's not going to give you a negative answer. It is simply a super cute disguise for a fraction.
Whenever you see a negative sign up in that index, just imagine it drawing a fraction line. You pop a 1 on top, and you move your base and the now positive index straight to the bottom. It's flipping the math entirely upside down.
Section 5. Conquering fractional powers. We've mastered the basics, we solved the zero mystery, and we unmask negative indices. Now we have reached the final boss of our explainer, fractional indices. Seeing a fraction floating up in the index spot can look absolutely terrifying. Just take a look at 16 to the power of 1/2. What on earth does it mean to multiply 16 by itself half a time? Well, before panic sets in, let's break it down together gently, using the laws we already know and trust. Let's run a quick little experiment. First, using our power of a power cheat code, what if we took 16 to the power of 1/2 and we squared it? We'd multiply the indices. 1/2 times 2 is 1. So the result is 16 to the power of 1, which is just 16. Now switch gears to standard math. What else do we know that when you square it gets you right back to 16? The square root of 16. If you square a square root, you get the base number. Because both of these paths lead us to the exact same answer of 16, it tells us something really amazing. Raising a number to the power of 1/2 is the exact same thing as taking its square root. So 16 to the power of 1/2 is simply the square root of 16, which is just 4. Now let's put absolutely everything together to defeat a monstrous-looking problem, the ultimate boss, 25 to the power of 3/2, a fraction with a number larger than 1 on top. Take a deep breath. You have the exact cheat codes to beat this. We can easily slice this monster up just by reversing our power of a power law. That fraction, 3/2, it's really just 1/2 multiplied by 3. So for step 1, let's rewrite it. 25 to the power of 1/2, all wrapped up in parentheses, raised to the power of 3. Suddenly it's not so scary. Moving right to step 2, we just learned that the power of 1/2 is literally just a square root. The square root of 25 is a very friendly number 5. And finally, step 3, we just take that 5 and apply the outside index. We cube it. 5 times 5 times 5. And boom, the final boss is defeated, bringing us right back full circle to where we started this explainer, with a beautifully simple 125. You just calculated a complex fractional power in your head using absolutely nothing but logic and structured rules. It really is that straightforward when you have the right tools. We've journeyed from basic definitions all the way to dismantling fractional powers, proving that math isn't about rote memorization. It's about discovering the underlying logic and applying the right rules. So, armed with these newly proven laws of indices, what other intimidating, seemingly impossible math problems out there can you turn into absolute child's play? For instance, what do you think happens if the index isn't a fraction at all, but a letter, or even an irrational number like pi? Keep looking for those cheat codes, keep exploring the logic, and I'll catch you in the next explainer.